One, Section 311, related rates. As I mentioned, one of my favorite sections because we get to write some mathematical models, do some analysis, calculate the future, and so on. So first of all, let's discuss the title, related rates. So first of all, we have rates. We said that derivatives would measure the rate of change. So here's the word rate again. And if I have the word in plural form, which means rates, that means that we'll have multiple rates that are changing, and we can measure them and observe them, and then they are related through some kind of equation. So I want to start with the most basic idea. We all hopefully understand that if you take the ice cube, and I'm going to keep it as a cube, so none of the fancy shapes, it's just going to be, let's say, inch by inch by inch cube, and you leave it on the sun, it's going to melt, all right? So it is changing what? It is changing its volume, it's changing its surface area, it's changing its sides, which means it's changing and it's becoming smaller. So we can start by just looking at that basic problem to understand the concept of the entire lecture. So let's say here's a cube. The side of this cube, let's call it A. So it's a cube, so all of these are A's. And what we know from the previous courses in geometry and so is that the volume is A cubed. We know that the surface area is going to be 6A squared because we have 6 sides to the cube and they're all the same, A squared. It's a three-dimensional object, so we do not talk about perimeter, right? That's only for 2D objects. So we have this cube. Now I want to put this cube in an environment where, let's say this cube is ice. Let's say that it's a very hot day and it's going to melt quickly. And I'm going to try and figure out what is the relationship of, let's say, change in volume to the change in the side. Because it should be clear that if this cube starts losing the length on all the sides, that the volume will decrease, and that should be common sense. So in that sense, what I can do is I can take this equation here and I can differentiate it in respect to time, because all of these changes happen in time. And this is where you immediately realize that the variables that we have do not match, which means a whole bunch of chain rules are going to come into the game. Volume is the variable v, a is the length of the side of the cube, and then t is the time. So none of those match, which means that every time we take the derivative, chain rule is going to pop up. So what is the derivative of a v in respect to t? Well, the derivative of v is 1, and then you have dv dt from the chain rule. So we start with dv dt is equal to. Now, what is the derivative of a cubed? 3a squared times dA dt, which is the chain rule piece, because a and t are not the same variable. Now, looking at this equation here, this is what we call the mathematical model, and it is related rates. You see the plural rates there with s at the end, because you have a rate on the left. It is the rate of change of volume, and on the right is the rate of change of length of a side. So you can see that they are related by this times 3a squared. So related rates really fits as a title as you look at this and all other equations. So now I would like to spell it out, that this one over here is rate of change of volume, and this one over here is rate of change of the length of the side. So now if I know any of these numbers, I can compute the other. We can also do the same thing for this equation, because again, if I take the derivative in respect to time, I will find that the change in area over time is going to be 12a dA dt. Remember, every time when we're taking the derivative of a in respect to time, we have to follow with the chain, or the area, or the volume, or whatever else we do later on. It has to be differentiated. So this is going to be another formula. You are not memorizing these formulas. These formulas are all obtained by simply differentiating and using the chain rule. What you should know is the area of the circle, the volume of the sphere, those are types of equations from, high school geometry that you should, and pre-high school geometry that you should know. The rest is going to be basic derivatives with the chain rule that will actually be getting you these boxed equations. So this is what we have for our equations. And as I said, as long as you know any of these equations, you will be able to compute things that you are interested in. So now the textbook is talking about the oil rig, which is leaking oil into the water, and as that happens, it circularly spreads around. So this would be something that environmental scientists will be looking at, because you want to see what is the rate of change, because rate of change is technically how fast will this oil spill progress. And it progresses in circles, right? Because the epicenter, the center of the whole spill, is where the oil rig is, and then the pollution around that rig is growing in all possible directions because it's ocean, right? So it spreads evenly, unless it's on some kind of, stream or a current kind of spot. But then, for the most part, it's going to be spreading evenly in all directions. So technically, what you are looking at is the center where the oil rig is, and let's say I don't know, after 5 minutes looks like this, and then you wait 10 minutes and it looks like that, and then 15 minutes, right? So it is growing, right? The pollution is growing. So now, how would you write the mathematical model that would measure this? Well, you start by figuring out what you need. Are you trying to see how fast is the circumference rising? Because you can compute that. Obviously, the larger the circle, the larger the circumference. Or you're trying to see how fast is the area growing. So maybe you want to know what is the square footage or the square mileage of the area that is polluted and how fast it actually grows. So let's start with the area. Area is the pi r squared. This is something that you should know from elementary school. And now, what we are doing in calculus is we are going to differentiate that in terms of time, because you want to see how the system evolves in time. So again, dA dt is equal to 2 pi r. That's the derivative. R squared is 2r, right? So 2 pi r, and then you have dr dt. Every time when the derivative is taken, you have to make sure that the variable that you are taking the derivative in respect of is matched or not matched with the variable in the problem. So I call it the dimension mismatch because you have an area and a time. It's not the same variable, it's not the same concept, physical concept. So we have to follow with the chain rule. Same thing goes on the other side with the radius and time. Radius is length, right? Time is time. So they're not the same concept, not the same variable. Therefore, again, chain rule has to happen. So now I have a mathematical model here, and it relates the rate of change of area in time to the rate of change of radius in time. And you can see that the larger the radius, the faster the area grows, because they are proportional in this case, proportional to 2 pi. Now, obviously, later on, you're going to get some numbers, and you just plug those numbers where they belong. So let's take a look first at, so these are some prerequisites, and hopefully you guys understand what is this lecture all about. Now let's first review some of the geometry equations that you are expected to know, because again, this is your elementary or middle or high school at best, or at worst, whatever. So what kind of formulas you guys need to know? Well, clearly, you need to know for 2D, you need to know everything about the circle, triangle, rectangle, and the square. That involves perimeters, that involves areas, because those are the concepts that you guys will be writing down as formulas. So for circle, area is equal to pi r squared. The circumference, which is the perimeter, is equal to 2 pi r. For the triangle, area is 1/2 base times height, and the perimeter is the a plus b plus c when you add them all together. For the rectangle, area is a times b. The perimeter is 2a plus 2b, because those are the all sides added together. And for the square, we have a squared, and then the perimeter is 4a as you add all of the values around the square. So that's the stuff for 2D. And as you can see, any one of these can be, you can take the derivative in respect to time, and you will be studying and observing how the systems change. So all of these could be smaller, larger, and that's what the calculus measures, right? That change. And now we want to get into 3D. Now, when you get into 3D, there will be some equations that we kind of don't have to worry about too much, because they're too specific or they're too annoying and long to memorize. So obviously you will be using reference when you start working to set up. And once you set up the equations, then Mathematica can take over from there. So we're going to start here by splitting the world of 3D into two groups. We'll split this into a group of cylinder-like or prisma-like objects, and the group of what I call spiky objects. So in this group over here, we're going to have, let's say, a cylinder. We're going to have a box, right, the 3D box. So it's going to have like that. We can also talk about the pyramid with, I don't know, maybe square base or something. So, oh, no, that's spiky object. What else I can put the cube. I can't think of any of the, I don't want to involve trapezoids and things like that in bases and so on. So shapes like this. Now what you need to have here, and we are concentrating on volume mainly, is the area of the base times the height of the object. So this is the height of the object, and then area of the base. So they look like this. And jumping into the spiky objects, we can have a cone, we can have, let's say, a pyramid, and the volume for those will be 1/3 b times h. So if you guys are able to find the area of the base, which is 2D, then you just multiply that with whatever the height of the object is, and then if it's spiky, 1/3. If it's not spiky, don't worry about it. So you are responsible for this knowledge. And there is a special category. The special category sits only one object, and that's a sphere. So sphere has as the volume 4/3 pi r cubed. So that's the only one that is different than all the others. It doesn't fall into it. Yes? The surface area of the sphere would be the 4 pi r squared. Since you're asking, 4 pi r squared is the surface area of the sphere. Surface areas in all other cases will be, you decompose the object. So for the cylinder over here, you have the base and the top. Those are circles, so 2 pi r. And then when you open up the wraparound, it works out to be a rectangle, so it's the circumference times the height. And you do that with everything. The tricky one is the cone, which uses the arc length. But other than that, the rest should be easy. We are mainly concentrating on volume. There will be some surface area problems, but not that many. So let's solve a very simple problem. Problem 6 is called a shrinking square. It says the side of a square decreases in length at the rate of 1 meter per second. The side of the square decrease at the rate of 1 meter per second. So question A, at what rate is the area changing when A equals 5 meters? Part B, at what rate are the lengths of the diagonals of the square changing? So we start with drawing the square. We can draw diagonals right away because we know what they are. So here's our square. What are we going to do with this? Well, first of all, we want to understand what are the right formulas, because this is all it's given to us. We don't know anything else. And this is actually the stuff that you pick up in a meeting as engineer. You pick this up in a meeting, or you think of a concept, and this is what you pick up, and now you're supposed to create equations. So what you see there? It says, at what rate is the area changing? So as soon as you see the area, and you know it's a square, you must start, common sense, right? Must start with area equals a squared. So that should be common sense, because the word area is mentioned and the word square is mentioned. Now, you are also picking up in this problem words rates, which means, and you also see at what rate, right, is changing, and you also given meters per second, so you see that the units are over second, which means change in time. So you immediately say, I am differentiating this in respect to time. Well, all of the problems will be differentiated in respect to time here, but you know, because you are measuring how fast is something changing, moving, or whatever. And what you get here is the area, so dA dt is equal to 2a dA dt. This is your mathematical model for the problem because this equation relates the change of the area to the change inside, the length of the side in time. And now you plug in everything that you see. It says the side of the square decreases at the rate of 1 meter per second. So now, what is this 1 meter per second? What variable? We have dA dt as a variable, a as a variable, and dA dt lowercase, right? So what is 1 meter per second? Which one? Yes. We have two dA dt's. The lowercase, yes. It's the lowercase. Because it says the side, and little a is the side. Lowercase a is the side. So the side of the square is decreasing at the rate of blah, blah, blah. And then we also have from part A, we also have that a is the 5 meters. So now, all you need to do is to plug that in, and you will be calculating how fast the area is changing. It's 2 times 5 times 1, which is 10. Now it's area, so it's going to be meters squared per second. So if the rate of the change of the side is 1 meter per second at a equals to 5, it will be changing 10 meters squared per second. Yes?
How do you get the 1 meter per second for dA over dc?
That is given in the text. Now for part B, we will have to do a little bit more work because diagonals will have the formula. So now I have the diagonal, and we take a look at the diagonal there. We try to figure out what is the equation for the length of the diagonal in respect to A. Now you either know this by heart, or you would actually have to suffer through Pythagorean identity to figure it out. So d squared is equal to a squared plus a squared, because, right, it's a triangle and both sides are a, and the hypotenuse, which is diagonal, is d. So that's 2a squared. If you square root both sides, d is equal to a root 2. Now you either know this formula, or you get it right there. So now we take the derivative of that one. So at what rate is the diagonal changing? So now we take the derivative, well, dd over dt is equal to square root of 2 dA dt. Remember that the derivative of a is 1, and then times dA dt is a chain rule. So now this is our mathematical model right here. We still have that this thing is 1 meter per second because it's still the same problem. And we get that the change in diagonal over time is square root of 2 meters per second. So if the side grows 1 meter per second, diagonal will grow about 1.4 meters per second. Green? So think about it. Yes.
Can you just go over the section B again? Just the B part of the muscle.
Sure. I even get up for the occasion. Here's a square, diagonal or a square. We'll label that D. Would have used capital D. And I don't have the equation for it, so I need to come up with it. It's a right triangle, therefore Pythagorean theorem will work. So a squared plus a squared is equal to d squared, and that's 2a squared. And if I take square root of both sides, I should get plus and minus, but lengths are never negative, so throw a minus away. Square root of a squared is just a, and I have square root of 2. So this is the equation to calculate the length of the diagonal if you know the length of the side of the square. So now I differentiate that equation in terms of time because I want to find related rates. What rates? A rate that measures the change of length of diagonal to the rate that measures the rate of change of the side of this square. Hopefully you understand that if I shrink this square, if I make it smaller, you can see the blue line over here, the diagonal is shorter, right? So if this, but it's not studied case by case. This is actually the continuous ongoing thing. You're actually looking at that square shrinking slowly. And because, or fast, doesn't matter. So as it's shrinking, the diagonal is shrinking as well. So we are measuring how fast the whole square is shrinking because of the side shrinking. And because that motion is happening, the diagonal is shrinking as well, and we want to know how fast the diagonal is shrinking. There's application for that somewhere, right? Right now we're just doing a geometry problem, applying calculus to it to figure out the equation. But you're going to see some awesome examples, and I'm going to go into business, and I'm going to go into all of these other things that will make much more sense. Yes? Yes, because we're taking derivatives, so yes, they're all instantaneous changes, and then you are taking a snapshot in time because you say when A is 5, how fast is changing at that point, and that will be calculated up there and calculated down there. So we see over here that once I took the derivative, I came up with a mathematical model. This is given in the text that it's 1, so 1 times square root of 2 is square root of 2 meters per second. So if each side of the square is shrinking 1 meter per second, the diagonal is shrinking square root meters per second, which is about 1.4. Right? Alright, so now I have to increase that because calc 2 gets to be like negative 30. Yes?
So when you're taking the derivative of E right there, and dAdt is the chain, right? That's
Yes.
the chain.
Because I took the derivative of A,
Yeah.
derivative of A is 1, but then I have the ADT.
And why does it just stay root 2? Why not?
Because it's the constant that multiplies it. What's the derivative of 3x? 3.
Okay.
So if it's root
Oh,
2,
gotcha.
right, root 2x is going to be root 2. So, the reason why I wrote the number after the variable is because, with sloppy writing, that A might be under the root, and then that would be a completely different problem. So that's why I wrote it in that. So let's take a look at other problems. All right, so let's see. Trying to find Trying to find a quick video. Awesome. Wow. Now, what you're looking at here is the SpaceX launch, but we are not looking at the automated camera, right? Look, the rocket is just gone. This is, yes. What the hell? So they're messing with these shots, but see, you can see that the camera is moving to follow the rocket, right? But the first few were really bad because, as you can see, the rocket is launched and it leaves the shot, and the camera doesn't follow, and you can definitely see which ones are the ones where the human is pointing the camera towards the rocket launch. So let's see, this one, I think this is the bad one. Yeah. So as you can see, the rocket is just going to leave the shot. Right? So what do you want to do, design as the engineer? Obviously, standing next to this thing as it launches and you know, recording it is not a good idea. The other thing is, if you're really far away, then all you see is just a little speck. You might want to design some automated system that is going to record the rocket launch, let's say, and that does not involve humans. It's going to have some kind of motor in it. On a bracket, you mount the camera on that thing, and the motor is going to lift camera, changing the angle so that the rocket is always in a shot. Difficult to make? The answer is hell no. Very easy, very cheap calculation, something that you guys should be able to do in a blink of an eye. And in that case, these kind of images, right, when it launches, the camera would actually stay focused on the rocket in the center at all times. I'm not sure if this is the video, because I watched this 5,000 times, all of the SpaceX stuff. One of them has a shot of a rocket, and they have a figure of Chuck Norris on the on the rocket, which is awesome. I don't know if you ever watch these, you should check them out. All right, so that's that stuff, and I'm going to now go back to the problem, and we're going to make up the problem out of what we just saw and use what we are learning today to solve the mathematical equation of what we need as specs of the motor that is to be installed. So let's draw the situation. So here be the Mother Earth, all right. Here is the rocket, right there. We are going to mount the camera not too far away. Let's say 500 feet. Mount the camera. It's an awesome camera. The camera is going to have a straight shot at the rocket. Obviously, the camera is capturing right like that, but we just do the middle line. Okay, I'm going to get rid of this. And the rocket is going to launch vertically. So this is going to be the height which the rocket is following. And then clearly the rocket should be followed by the camera at all times. I'm going to erase all of the midlines, so just keep looking at the screen now. The camera at one point will be pointing this way, and then that way, and then that way, and then that way, right? So as the rocket goes up, the motor on the camera will slowly increase the angle at which the camera is shooting so that the rocket is always in the shot. The speed at which the camera is recording has to be dependent on the speed of the rocket. Don't want to go angle too fast, not going too slow. We're actually going to tie the angle, the how fast the angle is changing to the speed of the rocket. Yes?
Since the rocket's constantly accelerating, and as it gets higher, even like as it gets higher, the change in angle will have to be smaller, right?
Yes, and all of that will be adjusting. So now we have these two. There is this angle theta over here. So now what do I have? If you look at this, we have the right triangle. And for the right triangle, what are all of the formulas that we can come up with? Perimeter, clearly useless. Area, clearly useless, right? Pythagorean identity, well, we are not interested in this length here, so that's going to be useless. And then we have all the trig ones. But the trig ones is awesome because that's exactly what I need. I need to relate that angle to the height over there. So by process of elimination, thinking about what are all of the formulas that are related to the right triangle, we eliminate area, we eliminate perimeter, we eliminate Pythagorean theorem. The only thing that is left is trig. Now you have opposite and adjacent, so tangent theta is the one that we are going to use as the height over 500. Now, what am I figuring out? I'm figuring out the angular velocity, which is theta over there, with the speed of the rocket, which is the change in height. So as soon as I differentiate this in terms of, time, we are going to get the related rates, which relates what we actually what we need. So what's the derivative of tangent theta? Very good. Followed by d theta dt as a chain rule. On the other side, we have a constant 1 over 500. We just get to copy that. And the derivative of h is dh dt, right? And then you can put 1 over 500 in front. That's just the constant. So now, what is the actual equation here? Well, the d theta dt is what we are looking for. So d theta dt stays here. On the other side, you have 1 over 500 times dh dt times 1 over secant squared theta. We just get rid of that because we don't need it on the left-hand side. Now, 1 over secant squared is what? Cosine squared. Very good. So d theta dt is equal to cosine squared theta over 500 times dh dt. Ta-da! This over here is the speed, angular velocity, at which camera should rise. This over here is the speed of the rocket. Computed at every angle, theta along the, right? So now what do we know? If you build a system that has the ability to change the speed of the motor that rises this camera up, and you know the speed of the rocket at all times because that's read on the computer, right? You can use that as the input for the controller that would adjust the height of this, the angular velocity, which addresses exactly that issue that as the rocket is further away, the camera needs to slow down. Because the rocket is going to shoot from here, it's going to go very fast up from this point, so this has to go really quickly up to follow the rocket, and then it's going to be slowing down. But all of those parameters that are there, that the controller is receiving to operate the motor, is going to use these two inputs, right? The camera will at all times know what's the angle for it, so that goes there for theta, and then the speed of the rocket will constantly be updated. So those two pieces of information will constantly be fed into the controller, and the controller will be sending the signal whether the motor should slow down, speed up, or whatever. And as the rocket progresses, the camera will always progress with it and have the perfectly still shot and centered shot for the entire launch. That's how awesome this section is. This can be actually designed. And Math Lab was actually 2 years ago considering to do this, except we would not launch this type of rocket. We would either do those water rockets or the air propelled ones. They shot a few of those at our soccer field up there, and they were thinking to actually use this Calculus 1 concept with the controller and build this kind of thing. And then they got sidetracked and started working on other projects. So this was never built, but it was one of the problems that were considered to be built. And it's not a big deal to actually make something like this. The hardest part actually would be to measure the velocity because, right, the SpaceX rocket has all the sensors and everything, so they know exactly how fast it's going at all points. In time, we would have to actually spend a considerable amount of time getting that information from the rocket that is not, right, they have no electronics on it, so all of that stuff will have to be added and engineered in addition to stuff. So that's technically what it is in terms of this problem. As I said, the idea over here is not just to go and regurgitate numbers and find the answer 7. It's actually to have this concept because you as engineer, you come up with this, right? And once you have this, then you and the computer scientist and all these you guys sit together at a meeting and say, we're going to input this into the controller, we're going to input that in the controller, and so on. And then what are the specs on the motor that you need, and what are the specs, right? So those are the things that you are working on as the engineer. No one will ever ask you to compute any numbers for something like that. Why? Because you have computers, exactly. It's a waste of time for you to sit there and compute for every single degree, right, from 0 to 90, of how fast it should move, and then program that by hand. We have controllers for that. And we have a computer to compute the input information. So all of this will be grinded. Your job is to find the equation. Now, obviously, for test purposes for this class, it's more like this problem, where you actually get square root of 2 as the answer, and move along. Let's take a look at more problems. Let's find some of the stuff. Let's solve more of the homework exercises. So we already talked about the cube, shrinking cube. Let's take a look at 14, which is piston compression. By the way, all of the problems are word problems. So we have a cylinder. And then there is a piston, which is something that you push in and you can compress. Let's say if this is air inside, it has certain density over here, and then as you decrease the volume, the pressure goes up, right? You should know that formula from physics. For some reason, people always remember that formula, and most of the other formulas are evaporated. The ideal gas formula. Right? The relationship between the pressure, volume, and the temperature. These both are constants. So now over here we see that as we are making the you can move the volume to the other side, let's say. So if I move the volume like this, then you see that the pressure and volume are inversely proportional, which means that the higher the pressure, the lower the volume, the lower the volume, the higher the pressure. So as you are pushing this in, this piston, the volume of the chamber will be less, and because the volume of the chamber is less, the pressure is higher. The cars work on the opposite principle of this. You inject a little bit of air, you inject a little bit of fuel from these two sides, and there is a spark plug in the middle, and that creates the explosion, which pushes the piston up. And then when the piston up, then you rotate the shaft, and then that translates into the motion of wheels. A very simple process out there. So this is the piston. They say that the radius of the piston is 5 centimeters. A piston seated at the top of the cylindrical chamber with a radius 5 centimeters, when it starts moving into the chamber at the constant speed of 3 centimeters per second. So it starts moving, so the speed, so I'm going to have some kind of, let's say, dy dt of 3 centimeters per second because it's moving down. This is the height y. So I said dy dt because it is the vertical motion, so that's the velocity, it's the speed at which it moves. And then it says at what rate the change of the volume of the cylinder. So the rate of change of the volume of the cylinder when the piston is 2 centimeters away from the base. So 2 centimeters away from the base. So it gets, let's say, there, and that is 2 centimeters distance. What would be the volume? All right, so I'm going to erase this equation because it's not relevant. We need the volume for the cylinder. We said that's a non-spiky object, which means area of the base times the height. Area of the base is pi r squared times the height. In our case, we call that y, which is the height of this piston. And now I'm supposed to differentiate this, and then in terms of time. So what do we see here? We see that the volume is dv dt, and then on the other side I have the radius and I have the y. Now radius is constant, it's always 5 centimeters. So I actually don't have to take derivative of that. But I do have to take the derivative of y because that will be changing the height. So I get to leave it as pi r squared, but then this one becomes dy dt. And this is our model. I have everything that I need to compute this. So the change in volume dt is going to be pi, and then the radius is 5, so 5 squared, and the speed at which happens is 3. So 75 pi centimeters cubed per second. change in volume, so you have to have volume units divided by the time units. Observe that they also told us this piece of information that we actually don't need, 2 centimeters away from the base. For the piston, which is cylinder, it's uniform in a way in which it changes the volume. So we actually didn't need that 2 centimeters because at any height it will be the same. And you see that it did not play a role when we took the derivative anywhere. And the only reason for it is because it's a cylinder. Next problem, again another engineering problem, is the one where we get to take a look at the a little bit more involved problem. So let's get the conveyor belt here. Conveyor belt is moving all of the, let's say, sand or coal or corn, it doesn't matter. So the stuff is coming up along, right, and falls down on a pile. It creates a conical pile. Make sense? So as the stuff falls, the cone is going to grow. And it's going to get larger and larger and larger. And if you don't shut off the supply of whatever you are storing there on a pile, eventually it's going to reach the conveyor belt and start building up on it and then break it. Now these things are extremely expensive, so you don't want to do that. You want to design a system that is going to turn it off at some point. So we can, again, compute at what rate things change. What can I calculate? I can calculate at which, yes. What are the concepts regarding the cone? What are the changes?
The height.
Great. Rate of change of height is something that I can compute. What else? Rate of change of, yes.
Or let's say the angle never changes.
The angle never changes, yes. What else does change? So what are the other, I'm sorry?
Volume of the cone.
Very good, the volume, right? The amount of stuff. So height changes, so I can calculate dH dt. I can calculate change in volume. Awesome. So dV dt. What else I can calculate?
The volume of the space, the area of the base.
Yes. So what are the other ones? At least 2 more. Volume we already, well, that's the change in volume. We covered the volume, so the other 2 will not have that word. What else? So we have the change in height, and we have the change in volume. What else? Change in? Well, all of that changes in time. So if the change of volume in time, change of height in time, and then let's see another 2 changes in time. So what would they be? What else we didn't use there? Surface area. Very good. Surface area, change in surface area. So dA dt is another thing that we can look at. And one more. Yes, which is, yeah, but
You're looking for a word, but I don't know what word.
I used it like 5,000 times so far. The width. So the width.
Oh, the base.
The diameter and half of the diameter is radius. Yes, that's the one that you wanted to say. Radius. Radius. Yeah, I wanted to put the word radius. So, so we can find the rate of change of radius, rate of change of height in time, rate of change of volume in time, rate of change of surface area in time. So all of these concepts can be found, and we have equations to check those. So let's figure out the volume, because that's, I guess, maybe most interesting one. And this being the cone, as I said, is not going to be as easy as earlier. So let's first write the volume equation. It's going to be 1/3 base times the height. So volume equation is 1/3 area of the base is pi r squared, and then times the height of the object, which is cone in this case. Cool. Now we are going to take a look at this drawing we have. We're going to draw the height, and we see the first radius and the first height. But then the radius changes and the height grows, and the radius changes again and the height grows even more. So now we realize by observing the picture that volume is a variable and the radius is also variable because it changes, and the height is the variable because it always changes. That means that when we take our dv dt now, we have a product rule on our hands because they're all variables now. So I have pi over 3, that's constant, and then I have to take the product rule for the rest. Copy the first, which is r squared, times the derivative of the height, which is dh dt, plus copy the height, and then times the 2r dr dt, which is the derivative of the first. And then we clean it up a little bit. We have dv dt is equal to pi over 3 times r squared dh dt plus 2rh dr dt. Now I know you can factor out one of the r's in front of parentheses, but you're not accomplishing much, so we can leave it. So as you can see, the mathematical model for this one is more involved than any of the previous ones we had. But then again, it's cone, right? So a lot of things change as cone changes its volume. Again, you pick up in the problem what's given to you, and then you plug in, and then you see if you have enough. So let's take a look at, I believe there is a problem somewhere with the cone, not that one. Oh, it's in the sand pile. Okay, fine. So it's an example, so it's already done in the textbook, but too bad. Sand falls from an overhead bin accumulating in a conical pile with radius that is always 3 times its height. Radius, so this is what's given in a problem, given. Radius is always 3 times the height. It says that if the sand falls from the bin at the rate of 120 feet cubed per minute. So I'm going to write this as 120 feet cubed per minute, and then I'm going to see what is that. So what would that be? What would that be? dv dt, very good. dv dt, why? Why dv dt? But how do you know that? Nah, cube. Nice. You know that because of the units. The units are cubed. All of the area units are squared. Centimeters squared, meters squared, inches squared, right? You are looking for the square footage of the house, right? Because it's how many square feet? That's area of the floor, right? So all of the area units are squared. All of the volume units are cubed. Inches cubed, meters cubed, and in this case, feet cubed. So we have dv dt. So they didn't say anything. It just said the sand falls from the bin at the rate of 120 feet cubed per minute. So you have to know that that is the change in volume just by looking at units and knowing that all the squares one are areas and all of the volume ones are cubed. And then it says, how fast is the height changing? Now this is the way for me to write how fast. See, change in height. And the word fast is encoded in that time, the dt part. So how fast means d dt, take the derivative in respect to time, and then of height. So how fast is the height changing in respect to time? So that's dh dt, and how fast also, that's the wording. when the pile is 10 feet high, so height is 10 feet. Well, I have my formula. All I need to do is to plug everything in. dV dt, that's coming in 120. Good. Equals to pi over 3, open parenthesis. I don't have R anywhere. Ah, so 3h squared. Thank you. dH dt, well, that's what we are looking for. Awesome. Plus 2 times, oh, there's R again, so that's 3h. And then times h. And then I don't have the R dt either. Next problem, huh? If it was just that simple, huh? Differentiate. So dr dt is 3 dH dt. And you probably were to say this thing, that if they are constant apart, then their rates will be 3 times apart. Yeah. So 3 dH dt. Clean up the algebra, solve by dH dt. The rest are numbers. You have everything. So this becomes 360 over pi equal to 9h squared dH dt plus 918h squared dH dt. Did I do that right? 3 times 3 is 9 times 2 is 18h squared dH dt. Awesome. Wow, these are the same, so we add them. So 360 over pi. 9 plus 18 is 27. H squared dH dt. Now we know that age is 10, right? We have that. So plug that in. It's 100, so 2700. So 360 pi over pi is 2700. dH dt, from where dH dt is what? 360 divided by 2700 times pi. Cancel zeros. 36 and 27 divide by 9. So we get a 4 and 30. And then they also divide by 2, so I get 2 over 15 pi. Feet per minute. Pi is about 3, so it's about 2 over 45. This will be considered a spicier example because you have a lot of these. First you had the product rule, and then you had that tricky relationship between R and 3H that you had to utilize and also take derivative of to plug things in. So study that example. Project will be uploaded this weekend for you to work on. I believe 3 problems, and they are due the day of the final exam, so you have 3 weeks, and don't mess with it. Start immediately. It's not featured this year, but I have quite a few problems on the rotation, and one of them is to figure out how fast the melted ice cream would drain from the cone, the ice cream cone. And the amount of ice cream is given to you as a scoop, which is the sphere, and it all melts into the cone. So it's all about this. You have the transfer from the sphere into the cone, and then on the cone on the bottom, very unfortunate, there is a hole, and all of that precious ice cream is leaking through that hole. So that's one of the project questions. Those are kind of project questions that I like. Something that is applied. It doesn't necessarily has to be, nuclear physics. Stuff that all of you can relate to and work on, have fun, and maybe eat. Another problem that I had I already mentioned that a few times in the class, was the Newton's law of cooling, which calls for you to bake. You can actually do the experiment, or you can get in a group and do one experiment. That's that famous the chicken baking thing that I told you. So you can do the Newton's law of cooling and actually verify all of the equations and calculations that you do in the setting, right, while you are baking the chicken, and then later you have the feast and you just eat the whole thing, right, with friends. So those are the project questions. I will upload the project this weekend along with all of the notes that are missing. The Lion's Den is fixed. We got the email. It wasn't working last weekend, and they were supposed to have it done on Tuesday. Didn't work out, so they had it yesterday fixed completely. So after this lecture, I'll be posting all of the materials and posting the project so you guys can start on that. The project is that 10% free grade, remember? So you really want to put your back into it. 3 problems, they're all applied. Some of them have, measurements and things that you actually do, and take pictures and put all of that in a report. And it should be, something fun to do, especially if you like, formatting and designing things and so on. There'll be some math as well to calculate things. All right, so we did a whole bunch of these problems. Yeah. If you really want to challenge yourselves, check out problem 19. Hours of fun if you don't know what's going on. Yeah, it is. So how long will it take to fill this swimming pool? It's something that you as engineer who designs swimming pools has to know, because that is one of the specs that goes on the info sheet as the pool is sold. How fast can you fill it? How fast can you drain it with the included equipment? Right? If you have an empty pool, it's not like switching the light switch on and the water is right there. Right? It takes time. How long? So it's in this section. The rate of flow, see the inflow rate of 1 meter cubed per minute, and then you are supposed to figure out stuff. So that would be a challenge question, so you can enjoy that one. A lot of stuff: rate of drive of submarine, altitude of the jet, draining a water heater, draining a tank. There's something with baseball. I'm always freaked out about those things because I don't know any of the rules for the game, so then I get something wrong and everyone yells at me. So I kind of avoid anything that is baseball related, but then you might like that. Oh, ladder against the wall. That's a cool thing. I forgot about that. They're fun. So you have a, well, first you start with Mother Earth. Then there is a side of the house with a roof. There's a gutter over here. Then what you do is you put the ladder like this with a fixed length. Let's say it's a 25 feet ladder. Sounds good? Or shorter? What should I put? 15 feet ladder? 15? And then someone goes up, right, to clean the gutter. Here's the hat. And you see there's the point where the ladder touches the ground and a point where the ladder touches the house. So you set up the camera, casually walk up to the ladder, and you kick this point this way. You got yourself YouTube likes. and dislikes at the same time, depending on the landing. You can actually figure out the speed at which this point, hence the fellow over there, is going down. So you can calculate that stunt, actually. What do you know? You know that this is distance x, which means that this is going to be dx dt, the speed at which the ladder goes this way. And then you have this to be the height y, which will be dy dt, which is the speed at which the ladder goes down, because the ladder has the 15 feet length. And now, when you're looking at this problem, you go, okay, it's a triangle. Perimeter, useless. The area, useless. Trig, useless, because we don't have any angles. So what's the only one that is left? Area is useless. Perimeter is useless. Trig functions are useless. What's the fourth thing for triangles that we can do? Pythagorean theorem. X squared plus y squared is 15 squared. When you differentiate this, d dt, you will have 2x dx dt plus 2y dy dt is 0. And when you move dy dt to the other side, you get dx dt, 2x dx dt is equal to minus 2y dy dt, and you can cancel these 2's. You get the math model x dx dt is equal to negative y dy dt. Awesome. Look at the minus there. Of course, the ladder is going down, right? So that minus is there to show you the direction, that the y height will be decreasing. So now you can measure x and a y. You can measure how much you kick, right? Because dx dt is the initial velocity. How fast did you kick the bottom of the ladder? And that all impacts on how fast the other point goes down. So clearly, right, the higher the ladder, the right closer to the house and all that kind of stuff, there is you move these parameters. But the equation is here, and in text, 3 out of 4 will be given. You just plug them in. So what I say, a 13-foot ladder is leaning against the vertical wall. When Jack begins pulling the foot of the top ladder away from the wall at the rate of 0.5, so in the problem in the book, this is given as 13 and this is given as 0.5. And it says how fast is the top moving when the ladder is 5 feet from the wall. So this is given as 5 feet from the wall. And they're asking what is dy dt. So you have all of the information. You don't have y given, but you can find y because you have this relationship here. You have x, and you have this as 13. So you have 25 and 13 squared, 159. So you subtract that, and you can calculate y. So you plug x, 5. This is 0.5. This is whatever you calculated there. And you have dy dt, which is how fast it goes down. So what? 169 minus 25 is 144, so that is 12. Very good.
Did you plan it to work out like that?
No, it's textbook problem.
Oh, okay. I thought you said you just came with the number.
No, I came up with 15. Because there's no 13 per letter. You can find right 15 or 25 foot letter, but you're not going to find 13 one. They found numbers that would work, so you don't have to bother with calculating too much, but still. So if you look at the textbook example, those are the numbers that are given, and then you just plug them in where they belong, figure out that y is 12 through Pythagorean identity, plug everything in, and the problem is solved. So you should really try these Many of these examples, as many as you can. Do you want another one? Should we do another one with calculation?
I it was pretty bad that in a row the seven test is going to happen.
Yeah, let's vote on test. All right, so this is done.
I already did it. Gotcha.
No, we're gonna do it now. All right, so let me just stop the stream.